Good afternoon, morning, or evening. So today in day 3 of the fields unit, we're going to be looking at charging by induction, which we did charging by contact, and that was when we were using these electroscopes here. And what we're going to do today is we're just going to summarize charging by induction and Coulomb's law of charges today. So those are the two things we'll look at today in physics. So hopefully most of you guys are getting into writing your exam for the second unit on conservation of energy. I've got a number of the hand-ins yet, but you should be getting around that point now, depending on where you are. So think about that as well. Okay, so let's go ahead and do what we're going to do today. Set up here. And this will be, today will be day 3, field unit. And we're going to be looking at charging by induction, what happens. Unlike the last one, I'm only going to show you one of the induction methods, and the other one you can figure out because it's basically the opposite. So we're going to do charging by induction with either a positive or negative rod, and I'm going to leave the other one blank for you to figure out. And we're also going to look at induction in terms of two charged objects coming together, and then that'll lead us into Coulomb's law. Okay, so let's do the summary for charging by induction. So charging by induction, what we do is we bring you bring a charged object close to a neutral object. This forces separation of charge on the neutral object. Or if you like, a split of charges on the neutral object. Good. Then you touch the object, which is called grounding. If it's charged, if it's not charged, you're just going to put charges on it. Then you touch the object, and the neutral object will lose or gain some charges, depending on what happens. You take away the charged object that's close to the neutral object. Called the charging object. And your finger, then your finger, or your touch. Okay, as a result, the object is now charged, the opposite charge of the charging object, that the charging object was. So let's draw this out. It's easier to see as a diagram, but that's basically what we're going to do. So I thought I'd type it out and then draw the pictures. So here, we'll number them up in here as we go. So the first thing that we have, if we take our marker out here, we draw our electroscope leaves. Okay, so let's do a charge. Okay, this is neutral. Okay, and then let's do a charging rod that is positive or negative. No, let's do positive. Oops, there we go. So we'll put the positives on here. Okay, that's a positive charging rod. And our neutral electroscope. Okay, the leaves are not spread because it's neutral. Okay, there's no charge there. Okay, so what we do first, if we look up here, you bring the charge object close to the neutral object and it forces a split of charges. So the neutral object, in this case, if we bring it here, the neutral object, let's get this drawn here. So it's going to split the charges. So it is going to have some split of charge. And this positive rod is going to be close but not touching, right? So put the positives on it. So these positives are going to stay here. And positives don't move, so they stay in the same spot. And what happens then is the negatives get sucked up towards the charging positive rod because negatives move and they're going to be attracted to this rod. So we're going to see a concentration of negative charge right there. Let's say one here. So they're getting pulled up towards there. So what we see there is split charge. In this case, the negatives are getting attracted to the charging rod. Okay, once you do that, the next step is to touch it with your finger. Okay. It's attracted to the charging rod there. The negatives are. Put the negatives there. Okay, so then the third one, we're going to touch it with our finger. So we still have the charging rod here. We still have the split charge occurring here. Okay, these are spread apart because there is some force of repulsion there with the two positives there. Okay, so we still have the positive rod here. We still have the positives here. And we still have the negatives here. Okay, it's still neutral at this point. Now we take our finger, we touch this. Oh, let's do it in black here. Okay, so we're going to touch the object, and we have a bunch of different kinds of charges on us because what's going to happen is the negatives are going to get attracted to this positive rod that's close. So there's going to be some negative charges that are on here, let's say 4 or 5 or whatever, and they're going to get attracted onto, and they're going to flow through our finger onto the neutral object. So as we touch it, the charges are attracted onto the neutral object. Nope, I had it right the first time there. Okay, now that opposite would happen if this is a negative rod, the negatives would be pushed. They would be pushed away. They'd be down here. They'd be pushed onto your finger. So don't get mixed up. It makes a difference what the charging rod is, what's moving. Okay, you got to remember the law of electrostatics. So that charge, these negatives are there. So then we take our finger away and the object away in number 4. And we're left with a neutral, the neutral object changing to a negative object. Okay, so it looks like this in number 4. So in number 4, remove rod and finger, or touch if you like, and we've got still a charged object here. Okay, but it's going to have extra negatives on it. So we're still going to have our positives where they are, one there, one there, one there, one there, one there, and one there. But then the negative objects are going to be spaced out, and we're going to have the 6 negatives on plus these extra 4 that moved on. So we're going to have 10. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8, maybe 9, 10. And there's more negatives down here than positives, so that it's not going to be as strong as this one maybe. Maybe it will, depending on how much charge you manage to pull onto the object. It really depends. So you're going to have some repulsion there, and we're going to see the neutral object becomes charged negatively, or the opposite charge. Okay, usually I ask a question, I might ask the opposite one. What if we had a negative rod here? Now things will change. It won't be exactly the same. They'll get an opposite charge. Because if I had a negative rod here, instead of the negatives coming here, they would have been over here, and they'd be getting pushed onto your finger, and you'd be left with extra positives. And then it becomes charged by induction. So induction, not induction L. And that means that if it's charged by induction, that's what this is, this process is, okay? That's where it's going to have an opposite charge as the charging object, or charging rod, if you like. Okay, it's going to be the opposite of whatever you're holding close to it. Okay, because of the laws of electrostatics. Okay, so that is basically charging by induction. We did charging by contact. Now that was charging by induction. So our next little thing that we want to look at is Coulomb's law. Okay, I'm just going to pause here and set up my examples here for Coulomb's law, and then we'll look at Coulomb's law. Oh, before I do Coulomb's law, I was looking here at my notes. Thank God I did. We should do one more induction little trick. So sometimes there'll be questions on induction. So they'll say, let's say induction example problem. So this would be something that I might ask you, for example. Okay, so let's say 2 conducting spheres are neutral in charge. And touching each other. Okay. You bring, let's say, a negatively charged rod close to the first sphere. Let's call it sphere 1. A, we'll call it A. Close to sphere A. Then move sphere B away from A and take away the rod. And take away the rod. Okay. What charge will sphere A and B be? Okay. So there you have three chances. You have positive, negative, and neutral. Okay, there's three different charges: positive, negative, neutral. Okay, okay, and you could just state them out, but it's easier if you draw it. So let's draw it out here and see what happens. So, okay, if we have these two spheres that are conducting spheres and they're on an insulated base or whatever, so let's call this one sphere A and sphere B. They're touching. So here's A and here's B. And they're neutral. So neutral objects have equal charges. And remember, the negatives move. So let's put in 4 positives in each of the spheres. Okay? And 4 negatives in each of the spheres. Evenly spaced because of the laws of electrostatic charge, attraction and repulsion. Okay? So now we have both spheres. They're touching. That's step 1. Okay, then it tells us in the problem here. Okay. Problem 1. Okay, they're touching. Okay, then you bring a negatively charged rod close to the spheres, close to sphere A, so close to this one. So if we bring a negatively charged rod, which are the ones that move, close to, but we're not touching it, what's going to happen to both of these? Well, they're still touching. We're going to see, let's go change back to black here, draw our spheres. So here's A, really close, and B, still touching A. Okay, there's A, here's B. So what we're seeing now is this negative is going to repel other negatives. Remember, the negatives are the ones that move, so those are the ones you're interested in. So the positive charges are the same. 2, 3, and 4. Okay. And we're going to see the negatives. I should put the 4 positives in first. So we're going to see more negatives get pushed onto B. So they're going to go away from here. So what we'll see is maybe one negative stays here and a bunch of negatives go on this edge. So there's the 4, 5, 6, 7. So there's still 8 and 8 charges. But now they have split apart like that. Okay, so now if you look at the two spheres, Negatives moved over here. Now you're going to move sphere B away. So that was 2. And you're going to split them apart and take this rod away. So in number 3, A and B. So if you take it away, this is going to end up being a bunch of, it's still going to have its 4 positives on this one. Still going to have its 4 positives on this one. And now these 7 are going to kind of evenly space their way around here. And this 1 still over here. So what we then have is we have a positive A. Okay. Sphere A becomes positive. Sphere B becomes negative. Got the P in there. So that's an example of, I should maybe write the word positive instead of plus. So this would be 3 here when we have the 2 plate. So that's a typical example of an induction problem. Okay, so here they were neutral. You bring a negative rod in there. Positives don't move, but the other negatives, opposites attract, like charges repel. So they're going to get repelled over to the far edge. Okay, unless B was over on this side of A, right? Then A would become negative. I guess I should have said A and B are touching, because I guess you could have, A is in front of B, right? Because we could have, well, I guess if I would have put B on this side, then that would have been sphere A. So no, that's good wording. So then we pushed them all over here. Then when we split them apart, when we remove the rod and put them apart while the rod was still there, we move B back, it would have some extra negative charges on it, and A would have negative charges missing. Okay, and that's kind of a typical induction charge type thing. Now, if I said contact, different things would happen. If I said contact, different things would happen in the sense that they would probably both become charged the same as the rod, right? Because they're both, everything would be touching, and they would attain the same charges. So you have to be able to use the laws of electric charge rules to kind of figure out what's going on. So that's a typical example. Okay, so that was the second thing I wanted to look at. If we look back here, we're doing charging by induction. Oh, I forgot to write down the other thing. The other thing I wanted to look at is Coulomb's law before we get too far into looking at more charge type stuff. Okay, so again, I'm going to pause and dig up some Coulomb's law ones now. Okay, so our second part is we looked at basic elementary charging, but we want to look at what the size of the force between these objects would be. Okay, so that's when we get involved in something called Coulomb's law. Okay, so whenever we have 2 charged points, they're going to have some electrostatic force, even if it's one negative electron and one positive ion. You're still going to have some electrostatic force in between them. This is determined by Coulomb's law. So Coulomb's law, which we'll do on the next page here, relates the size of that force. So this is what we call and he came up with this guy named Coulomb. It relates the force of attraction or repulsion between two charged objects or points. Point objects is what we're going to talk about, because when we have larger charged objects, then Coulomb's law doesn't work for as well as it would, and we talk about electric fields, which we'll do later on. Okay, so this is a law. It relates two charged points we'll say point objects, we'll call them. So really point objects to the force of attraction or repulsion between the objects or the points, charged points. And so what Coulomb found was that it mattered, the size of the charges mattered. Okay, so first thing that matters is the size charges. Okay, the bigger the charge, the more the force. Proportional. Okay, directly proportional. If you have charges, is proportional. As charge goes up, the force goes up. That's the first thing that he found. Second thing that he found was it made a difference how far apart the charges were. So the distance between the charges okay, and these were indirectly proportional. Okay, they're indirectly proportional. And in fact, they're indirectly proportional to the square. Okay. Okay, distance goes up. So the farther apart they are, the charge goes down, or force goes down, sorry. Okay. Basically, that is Coulomb's law. And there's a proportionality constant in there, which is basically also the elementary charge. And he basically figured out how many coulombs are on, how many electrons it takes to make one elementary charge, which they call a coulomb after this guy. Okay, so the formula looks something like this. Really quite simple. And you'll find that it's similar to the law of gravitation when we get there. Okay, so the force, electric force, F. So this is force in newtons. Okay, and this is the attraction or repulsion, which is electro. So it's an electric force. Okay, is equal to K, which will Q1, little q, and Q2, they use Q for charges, over R squared. Okay, they use R for distance. So Q1 and 2, This is the charge in coulombs on each uh, on each object. Okay, there's two objects we're dealing with. This is the distance in meters between the two objects. Okay, and K is called the Coulomb's proportionality constant, which we're going to call Coulomb's constant, just because we don't need to put proportionality in there. We know it's proportional. And that is 9.0 times 10 to the 9 newtons meters squared over coulombs squared. Okay, and that's an example of, and this is a vector. So you got to be careful. We're going to do linear examples to start with, but you can have, just like we had when we did vectors at the very, very beginning in February, you can have right-angled ones, you can have different angled ones and things like that. So you have to be careful when you're doing these problems that they are proportional. Okay, so what we'll do today is maybe we'll do one example of two elementary charges that are not very far apart in a line. We'll go collinear line. Okay, so let's do an example here. Okay, so the first example we're going to do is of collinear point charges. Okay, now they usually use, because coulombs are a really big unit. There's one coulomb is a lot of charge. They use something called microcoulombs. Okay, so just remember that a microcoulomb. Okay, so we're going to use a lot of scientific notation. Okay, this means micro. Okay, just like you might have a centicoulomb or whatever, this is a microcoulomb. And you're like, okay, well, that's great, mystery, but how many does micro mean? Micro in the metric system means times 10 to the negative 6. Okay, 1 times 10 to the negative 6, or times 10 to the negative 6. Just like centi means times 10 to the negative 2. So that's 6 decimal places. So therefore, if I said you had negative 6.3 microcoulombs, this would equal negative 6.3 times 10 to the negative 6 coulombs. Okay? So we're going to use microcoulombs quite a bit in our notes. Okay, so let's do an example. Let's do a collinear example now. Let's say that we have this point charge and say it's negative 6.3 microcoulombs. And we have this charge that is positive 7.6 microcoulombs. And we have a distance between the two of 0.28 meters. Okay, so the first thing we got to do is we got to write our variables down and make sure they're in meters, coulombs for our equation. So these are in meters and coulombs. And we can use that equation and we'll get a force in newtons. So therefore, we'll call this one Q1, this one Q2, this will be R, okay? And then, so we know F, well, let's write them out in a list just for the first one that we do. So F is what we're trying to find. Q1 equals negative 6.3 times 10 to the negative 6 coulombs. Okay. Q2 equals 7.6 times 10 to the negative 6 coulombs. R equals 0.28 meters. We're good there. And K equals 9.0 times 10 to the 9 Newton meters squared over coulombs squared. Okay, let's make sure I got the right unit. Yes, I do. Okay, so we'll plug these in now. Okay, so 9.0 times 10 to the 9 for the K. First Q, negative 6.3 times 10 to the negative 6 coulombs. And 7 point. Now, you don't need to worry about the negative. All the negative and positive tell us in this is whether we're going to have attraction or repulsion. Okay? So this would be 7.6 times 10 to the negative 6. And then we're going to divide that by 0.28 squared. Okay, so when you're using a calculator, you have to be careful that you don't, for scientific notation, use scientific notation properly so that you're not putting a multiply sign in between these here, only in between these. Okay, so 9.0 scientific notation negative. Oh, sorry, positive. Pardon me. 9.0 scientific notation 9, so it looks like that on my calculator, times, and I'm not going to even bother with the negative sign, 6.3 scientific notation negative 6 times 7.6 scientific notation negative 6. So I get 0.430492 or 4.3092 times 10 to the negative 1 if you leave it in scientific notation over 0.28 squared, which I should work that one out. Let's work that one out. Okay, 0.28 squared is 0.784. Okay, and we're going to be left with newtons when we divide this out. Okay, and significant figures, we got 2, so we can round it off to 2 when we're done here. Oh, that seems a little high. Let me do that again. 0.43092 divided by 0.0784. There, 5.5 if we round it off to 2 significant figures, newtons. Newtons. Okay, and this is going to be, because it's opposite charges, it's going to be attraction. Okay, if it's the same charges, it's going to be repulsion. Okay, so that's an example of Newton's collinear law. Now we can also have some that are vectors as well, and we'll look at those later. The other thing we should do is the force is going to be an attractive force. Because of the opposite charges. If they're repulsions, right, they're going to be, the force is pulling them together, like magnetism of opposite poles, or like poles of repulsion. Same kind of idea. Okay, so that's about 41 minutes. We'll stop there today, and we'll save the second part for next day, which will be looking at Coulomb's law, a couple different examples, and non-collinear examples of Coulomb's law, so part 2.